Hi guys. In section 12.2, we're going to learn a little bit about pressure. Pressure is a little bit tricky intuitively because we think of pressure and force as being the same thing, and it turns out they're not at all. One example that points out this difference pretty well is the bed of nails, which unfortunately we don't have access to. This video is being made in April of 2020, and we're in homeschool. But if we were in S108, we would get down the bed of nails, and it's about 1,500 nails that have been pounded into a piece of plywood. And the idea is that you can lay on those 1,500 nails, and while it's not exactly comfortable, it doesn't necessarily hurt either. And in fact, you can even stack people up on that bed of nails without impaling the person on the bottom. The reason, of course, has to do with this. This denominator is what throws things off a little bit. Because there are so many nails, the force, your weight on a bed of nails, gets spread out over a fairly large area, and so you're able to lay on it. Another example that's often given is that if an elephant were to step on your foot, it feels the same as a woman in high heels. In other words, you exert the same pressure as a woman stepping on your foot with the stiletto over high heel. Why? Well, an elephant exerts a tremendous force. It's very heavy, but its foot spreads that weight over a relatively large area. Whereas a woman weighs much, much less, much smaller force, but in a high heel, that heel concentrates that force in a pretty small area. And so the effect on your foot turns out to be the same. And so here's the equation for it, for pressure, I should say. And the idea, of course, is that you can make any force tolerable if you spread out that force over enough area, and you can make tremendous forces if you concentrate them onto a tiny area. An example of that is businesses that make industrial diamonds. They use something called a diamond anvil, and by exerting pretty tremendous forces over a tiny, tiny area, they're actually able to squeeze carbon into a diamond. This is exactly what happens during, with natural processes of creating diamonds in the earth. I'm not aware of any distinguishable difference between artificial industrial diamonds and diamonds you'd pull out of the ground. If you ever do find a difference, let me know. I'd be curious to know what it is and why it's like that. Force comes in newtons, area comes in meters squared. There are probably applications where this isn't the case, but in our class, we're going to have newtons per meter squared. Pressure has quite a few different units. You can use newtons per meter squared. You can use atmospheres. At sea level on the Earth, you experience 1 atmosphere, or ATM, of pressure from the atmosphere above you. You can use torr, you can use bar, you can use millimeters of mercury. One that's commonly used is called the Pascal. Atmospheric pressure at sea level is right around 100,000 pascals. To give you a sense of context, if you were to go to Mars, you would feel something like 1,000 pascals. Mars has about 1% the pressure that we have here on the Earth. So this is pressure. Let's take a look at a couple of examples here. What they're showing here is you poke a person in the shoulder with your finger. Since the point of your finger has a larger area, they feel a smaller pressure. Right? Then, of course, you do the same thing. You use the exact same amount of force, and that's what's kind of key here. It's an identical force, but instead of poking them with your finger, you poke them with a syringe. That very small area works out to make a much, much larger pressure. All right. This says measuring density. That's actually a mistake. It should say measuring pressure. Excuse me. I apologize for that. What we have here is, it could be water, it could be mercury, but it's some kind of a fluid that's inside of a tube, right? And it's open to the atmosphere on both ends, and so both of these sides have to be at the same height. You can do tricks with this where you put alcohol in one side and water in the other side, and because they have different densities, these two levels don't match up. But we're going to assume that we have one fluid that has a uniform density, so the height has to match up here. Now we hook up a balloon, right? I don't know why they chose a Mickey Mouse head, but you hook up some source of pressure, like a balloon, and that balloon is going to exert extra pressure which of course is going to try to push the fluid up and out of the tube, right? And so that introduces a change in pressure. Okay, now we've got a few things going on here. The first, this is PG. P is for pressure, G is for gauge. Gauge pressure is the pressure in an enclosed space. And so it's the pressure between the fluid and the balloon here, right? So that's gauge pressure, and it depends on a couple of things. It depends on this H, which we're measuring right here. It depends on this rho. As you remember from the first section, rho is density. So that's going to depend on the density of this fluid, and it depends on the acceleration of gravity, right? Which on Earth we're going to assume is constant. So this piece right here is gauge pressure. The gauge pressure is only felt on this side of the tube. Now we have atmospheric pressure. Atmospheric pressure is felt on this side of the tube because it's open. You say, well, what about on this end? This is enclosed. That's true, but the atmosphere is pressing on the balloon, which in turn presses on this side of the tube. So both sides of the tube, the open end and the enclosed end, both feel the exact same atmospheric pressure. And when you add together the pressure of the atmosphere plus the extra pressure due to this balloon, that's represented right here, you get the absolute pressure. Here we have a different scenario, don't we? We have peanuts that are vacuum packed. It's a little bit odd. I'm not quite sure why they chose that particular example, but you can imagine a scenario, pardon me, where you have less pressure on this side. Now the gauge pressure is negative, which is just saying that the enclosed side of the tube is going to have a higher amount of, the fluid's going to rise up into this part of the tube. And that means that the enclosed part is negative. We have negative gauge pressure. Atmospheric pressure is still pushing on both sides. It's obviously pushing on the open side of the tube, but it's also pushing on this container, right? If you don't believe that, there are a number of ways that you can suck the air out of a container so that atmospheric pressure will crush the evacuated container. You can find that online or just look up how to do it. That's something you could do at home, although you wouldn't necessarily want to do it with plastic. It's much easier to do with a metal or aluminum container like a pop can. And so these are kind of the two possibilities. Either you've got both ends of the stick both ends of the tube open to the atmosphere, or you've got higher pressure on the enclosed end, or you've got negative pressure, so to speak, that is going to suck fluid up into the enclosed end. This is also sometimes called suction. Again, if we were in S108, there's some interesting demonstrations we could do with this, but it turns out that suction is, from a physics point of view at least, more accurately thought of as negative pressure. All right, this is a way to measure air pressure, right? And the idea is that we no longer have a tube that's open on both ends. We have a tube that has fluid pushed up into it, but the top is enclosed with a bit of vacuum here. In principle, this isn't going to be a perfect vacuum, but the idea is that the pressure in here is going to be much, much less than atmospheric pressure. And as long as you can satisfy that requirement, you'll have a pretty good way to measure atmospheric pressure. What is happening, you can see right here, we've got atmospheric pressure pushing down, not just on the left side, but also on the right side. So atmospheric pressure is being exerted over the whole surface area of this fluid. Probably, well, I guess they're saying it's mercury, so we should call it mercury. But it could be water, it could be gasoline, it could be anything that's liquid. Right here, yeah, we know that the absolute pressure has to be equal to atmospheric pressure. Now, let's think about what happens here. If we can somehow turn up atmospheric pressure, we're going to push fluid higher and higher and higher up into this tube. If we could somehow dial down atmospheric pressure, say by bringing it up into a mountain or flying it up into the atmosphere, fluid is going to sink lower and lower and lower in the tube. And so what you've created is a way to measure atmospheric pressure. You would have to calibrate this scale somehow, but once you've got it calibrated, you can, in principle, measure atmospheric pressure at any point that you have access to. You could bring this underwater if you wanted. Now, That would change just a little bit. And in the next section, section 12.3, we'll look at how this would change if you brought it under water. But in principle, the same ideas apply. Finally, let's take a slightly closer look at gauge pressure. I said earlier that gauge pressure is what happens anytime you've got pressure inside an enclosed space. So what we're looking at in this picture is a tire that has extra pressure inside of it compared to outside. We're going to assume that we have atmospheric pressure outside. The question is, what if you also have atmospheric pressure inside? Will that keep your tire inflated? The answer is no, it won't. You have to have extra pressure inside that will push back against atmospheric pressure, right? In other words, to inflate a tire, you have to have some gauge pressure. And the more gauge pressure you have, the harder, the more you would push back against atmospheric pressure. In other words, the more the tube is inflated. So when you go to the gas station and you take out one of those little things to measure the pressure inside your tires, you're measuring gauge pressure. I might try to trick you with a question like, what's the gauge pressure inside a deflated tire? The answer is it's equal to atmospheric pressure. If you could somehow have negative pressure inside your tire, in other words, less than atmospheric pressure, the tire wouldn't be deflated. It would actually be sort of vacuum packed, right? The atmosphere would be actually crushing the walls of the tire. I guess the only other thing you can take from this slide is the idea that pressure is exerted in all directions. This is also different from force. Pressure is not a vector. And that's just slightly subtle. We say that something like temperature is not a vector because it doesn't point in any direction. You say, well, shouldn't pressure be a vector? It's pointing in all directions, but those are still directions. The answer is no, pressure is not a vector. Pointing in all directions doesn't count. Mathematically, it's the equivalent of pointing in no direction at all. So pressure is not a vector in the way that force is. Pressure will exert itself in every direction it possibly can. In other words, pressure exerts itself in every direction that the container allows. Yeah. And that's it for pressure. Thanks for watching.